Hi, Cleo.
Hi, how are you?
Fine. How are you?
I'm good.
All right. You got
Super
some
hot out.
pardon?
Oh, I was just saying it's super hot out.
It's ridiculous.
Yeah.
It's like scary hot, right?
Yeah.
I'm very concerned about our planet.
Yeah.
So let's get started. Let me go ahead and start the video and let's see if this camera is in focus. Uh, let's have your first question, right?
Okay. Um, I'm still having trouble with finding the transitive closure. So I
That's
was hoping we could do like an example with that again.
And we could even do the one from the, isn't there a problem in the review sheet?
Yeah.
Okay, so
Yeah, look at that.
that's the review sheet for chapter A, right?
hmm
What number problem is that?
I'm looking right now. Um, hmm.
I thought there was one in that group.
I'm trying to look for it.
I'll bring it up too and see what I can find. Huh, well, there's not one.
Yeah.
So let's do one.
I know there's one on WebAssign, but we can
Is
just
it,
do like an
yeah,
example.
yeah, let's do an example. Okay. So, let me just take a peek here. Yeah, let's look at problem number 3
hmm
because it's a binary relation on, our favorite set, right? And it's given as R1. Do you see it, number 3?
Yeah.
Will you read the ordered pairs for me?
1, 1,
Uh-huh.
1, 4,
1, 4.
1, 2,
Uh-huh.
2, 1,
Right.
2, 2,
Okay.
2, 3,
Uh-huh.
3, 3,
All right.
4, 1,
Mm-hmm.
and then 4, 4.
Okay. So let's find the transitive closure. Well, as you look at these ordered pairs, we're going to look to satisfy the hypothesis of transitivity, right? And then
Mhm.
check the conclusion follows. All right. So we're going to check the hypothesis and then, we're going to look for that. And then the desired conclusion. And if we need to add an ordered pair, we'll put them here, okay? All right, so what do you see as you look at those ordered pairs? Hi, Chloe.
Hi Chloe. Um, 1, 4,
Mm-hmm.
and then I guess 4, 1, right?
Okay, so what would be the desired?
1, 1.
Mm-hmm. We have that one, right?
Mhm.
What else do you see?
1, 2,
Mm-hmm.
and 2, 3.
Okay, so what is the desired order?
1, 3.
And do we have that one?
No.
No, we don't have that one, so we're gonna add 1, 3. Great. Keep going.
2, 1.
All right. How about 1, 4?
Yeah, 1, 4.
What
So
do
2, 4.
we have 2, 4?
No.
We do not have 2, 4, so let's add 2, 4. Keep going.
2, 3.
2,
But
3.
I think that one's okay. Never mind.
Okay. Because the only ordered pair that has 3 as a first coordinate is one
Mm-hmm.
of these reflexive
Yeah.
pairs. We know we're not going to add anything from that.
Mm-hmm.
How about 4, 1, 1, 2? Have we done that one?
Not yet. It'll be 4, 2.
And do we have 4, 2?
No.
Well, we're going to add 4, 2. Anything else from what we see right here?
Um,
1, 2, 2, 3. Did we? Yeah, we did one. 1, 2, 2, 1 is 1, 1, and we have that one. Like we could write that down just for thoroughness.
mhm.
We need 1, 1, and we haven't. And if we wrote them in the other direction, did we already do that? 2, 1, and 1, 2, crossing over on the 1. We need 2, 2, but we have that, so that's good.
Okay, so you are supposed to like go backwards, right?
Now
Like we just did.
we're going to add these now and then see what else we need to check, right?
Okay.
This is like round 1.
So do you always have to like flip it
Mm-hmm.
and check? Okay.
Mm-hmm. Because the and operator, doesn't care which comes first, and depending upon which we put first, it might result in, a different ordered pair needing to be added, right?
Yeah. Okay.
Let's see, anything else? 1, 2, 2, 3. Oh yeah, we already said that like 3 times. 4, 1, 1, 4. We did 1, 4, 4, 1, and we had 1,
Mhm.
1. We have 1, 4, 1, and 1, 4 in that order. Crossing over on the 1, we need to see 4, 4 for transitivity to hold, and we have that one. I think we've got them.
Okay.
All right, so now our updated early R1. All right, so we have 3 to add. So now we have 1, 1. We're going to add 1, 3. We have 1, 4, because these aren't quite in order. 1, 2. We have 2, 1 already in there, right? And 2, 2 and 2. Wow, look at that. And 2, 2 and 2, 3. But now we need to add 2, 4. It's getting big. And
Yeah.
we have 3, 3 and 4, 1. And we're going to add 4, 2. And we have 4, 4. And now we play the game again. It's a lather, rinse, repeat situation. We had to add 1, 3, 2, 4, and 4, 2. And now we're going to go through this process again, where we're going to check to see if we have the hypothesis of transitivity satisfied. And then we're going to check for the desired conclusion and see if we need to add any more pairs.
Okay.
Mhm. So we can just scroll up at this point, right? We know that the underlying set is 1, 2, the set with 1, 2, 3, and 4 in it.
Mhm.
All right, so let's see. We know we don't have to worry about 1, 1 because it's never going to, make transitivity go bad. So we don't need to involve it in any of these checks for the hypothesis. All right, how about 1, 3? Because that's a new one, right?
Mhm.
What would be an ordered pair that has 3 as the first coordinate?
3, 3.
And that's not ever going to make transitivity go bad. So 1, 3 is not going to make us have to do any more work.
Okay.
Now let's move over. Actually, yeah, let's just move over to 2, 4. We really just need to check these new ones, right?
Okay.
So 2, 4 is a new one. And if we write it first, then we're looking at for ordered pairs that have 4 as the first coordinate. So let's check. 2, 4 is in the relation, and 4, 1 is in the relation, right?
Yeah.
So we'd be crossing over on the 4. What order pair are we looking for?
2, 1.
And don't we have 2, 1?
Mhm.
We do, so we're good there. What other elements have 4 as the first coordinate so we can check against 2, 4?
4, 2.
All right, 4, 2. Crossing over again on this middle coordinate, second coordinate of this order pair, first coordinate of this order pair. We're looking for 2, 2, right? Do we
Mhm.
have 2, 2? Because this is a reflexive relation. We've got 1, 1, 2, 2, 3, 3, and 4, 4. So that's so far so good. And then the only other order pair that has 4 as the second coordinate, excuse me, as the first coordinate is 4, 4, but we don't need to worry about that one. Oh, So that's when we put 2, 4 first, right?
Uh-huh.
Um, we'll come back and put them second. Let's go ahead and do all these where we're putting the new order pair first, and then we'll go back and put them second. So 4, 2 now. So 2 would be the crossover element.
Could do 2, 1.
Okay, so 4, 2 is in there now, and 2, 1 is in there. Crossing over on the 2. What are we looking for?
4, 1.
Do we have 4, 1?
Mhm.
We do. Okay. What about 4, 2, and what's another order pair that has 2 now as the first coordinate that's non-trivial?
2, 3.
Yeah, 2, 3. So we're looking for
4, 3.
4, 3. And we don't have 4, 3, right? So now we're going to have to, in this round 2, we're going to add 4, 3. And then 4, 2, and we check 2, 1. We don't have to check 2, 2. We check 2, 3. We can go ahead and check 2, 4 just mentally. 4, 2 and 2, 4 requires 4, 4 maybe for the completeness of notes, but we know we've got 4, 4, right?
Yeah.
So we don't have to add anything from that comparison. But now what if we put these new ordered pairs 1, 3, 2, 4, and 4, 2, not as the first ordered pair, but as, you know, where we're doing, but as a second
Mhm.
order pair. Like, is there anything where we could put the 1, 3 as the second ordered pair? What kinds of ordered pairs would go here? We're going to be crossing over on the 1, right? So we would need a 1 here for this to have any significance.
1.
We don't need 1, 1, right? But 2, 1 we need, right?
Mhm.
And then we're looking for 2, comma 3, but we've got that. So far, so good. Anything else ending in a 1 that's not trivial?
4, 1.
4, 1. So let's check 4, 1 and 1, 3. What ordered pair do we need?
4, 3.
And we've already added that, right?
Mhm.
So no, it's not in there yet, but we're getting ready to add it. All right, let's do the same game with 2, 4. So putting the 2, 4, not first, but second.
1, 2.
Okay, so 1, comma 2, crossing over on the 2, we would need 1, 4, and I think we've got 1, 4.
Mhm.
What else?
4, 2.
Okay, 4, 2 and 2, 4 are both in here. All right, and that would mean we need 4, 4, right? But we've got it.
Mhm.
Anything else with a 2 for the second coordinate? I think that's it.
Yeah, I think that's it.
Right now, we're going to put the 4, 2 as the second ordered pair. So we're looking for ordered pairs that have 4 as the second coordinate. So
4.
1, 4. So we would be looking for 1, 2, but we've got, do we have 1, 2? Yes, we do. It's not in the right order, but there it is. Great. What else with 4, 2 as the second ordered pair? Something ending in 4.
2, 4.
2, 4. Okay. And we are actually already checked that one.
Mhm.
It's because, did we do this? Yeah. Well, anyway, so we've got
Oh.
that. Okay. It's all right. It's better to do too much than too little. This is redundant, but at least we know we're being really careful. Is the 4, 2 going to be involved with anything else? Something that ends in a 4? This ends in a 4, this ends in a 4. This ends in a 4, but we know we don't have to worry about that one.
Mhm.
So the only order pair now that we need to add here in round 2, this is our round 2, right? Is to update our R2. I'm going to try to put these in order now. 1, 1, 1, 2, 1, 3, 1, 4. So 1 is related to everything. 2, 1, 2, 2. Well, look at that. 2, 1. Starting to kind of look like A cross A, isn't it?
Yeah.
I wonder if we're going to have to, I think we're going to have to get all of A cross A. I don't know. We'll see. No, maybe not, because all we have here is 3, 3. But now we have all of the 4 X's, 4 Y's, 4, 1, 4, 2. We're going to add 4, 3 and 4, 4.
And
So,
then you have to go ahead and check again, right? For the new added pair.
so let's check this one against everything. So if we put 4, 3 first, the only thing that has 3 as a first coordinate is 3, 3, right?
Mm-hmm.
So we don't have to worry about that. So if we put 4, 3 second, however, so that we're crossing over on the 4, we're looking for ordered pairs that end in 4. And we have them all, right? So 1, 4, right?
Yep.
So what would be the element we need?
1, 3.
Oh boy, we don't have, do we have 1, 3? Oh, we do have 1, 3. Great. So if we put 4, 3. Second, what else might it satisfy the hypothesis?
2, 4.
2, 4. So we're looking for 2, 3, and we have that, right? We have 2, 3. Yes, we do. Great. 4, 3 on the right, and we don't have 3, 4, so we don't have to work. And we have 4, 4, but we know it's not going to matter,
Mhm.
right? I mean, just for, 4, 4 would never make things go bad because, I mean, I'm writing it here, but this is not needed. This check is not needed just for folks that haven't seen this lecture yet. Because whenever we have an ordered pair that's got the same first and second coordinate, like 4, 4, it's never going to make transitivity go bad. So I think this is our final RT. So our final answer, R2 is R2 that's been closed under transitivity is in fact this kind of interesting big relation, but it is not quite all of A cross A, is it?
So in the WebAssign, when they ask for the transitive closure, should we put the entire set and not just the sets and not just like the ordered pairs that we found?
Yeah, it should.
Okay.
I think so. I mean, that's the way I understand the definition. Why don't we
Okay.
go and check the ebook just to make sure? All right. So that's, always a good practice thing to do. Let's open up the ebook. Let me just grab that and I'll share my screen. Log in. I won't bore you with that. How's everybody doing out there? Chloe and Suleiman, you haven't had this lecture. No, Suleiman, you missed class. Are you going to come to lecture at 6 o'clock tonight?
Yeah, I am.
Good. We're going to learn this tonight. This is called transitivity. It's a property of binary relations on a set A. And that's our last lecture tonight. Let's take a look in the ebook and see. I'll share my screen.
Is it over Zoom, the last class?
Well, I've been teaching a Zoom class all semester, but not for you. I mean, not in your section, right? I've been teaching it in a different section. All right. For privacy reasons, I have not generally published those videos publicly. That, I give links to the kids in the class, but I did put links to the chapter 5 lectures just to study for this test. All right, so here we go, ebook. So we're going to look at what Epp says about transitive closure. We're in chapter 8, and it's properties of relations, section 2, transitive closure. So here's our definition. Oh, and she uses a little t. I use a big T. Doesn't matter. Let A be a set and curly R be a relation on A. The transitive closure of R is the relation RT on A that satisfies all these properties. It is transitive. The original set is a subset of RT. Yes, this answers your question right here, Chloe.
Mhm.
Cleo, sorry. Cleo, that the original set needs to be, we added elements.
Okay.
And then if S is any other transitive relation that contains R, then RT is contained in S. This third property is redundant. And a little bit obscure, which is why I did not include it. I included the first 2 parts of the definition because that's sufficient. You know how sometimes definitions are redundant. But here in this first example, right, it says here's the relation R on this set A that's got 0, 1, 2, 3 in it. Right? It's kind of interesting little set with 0. Here's our relation. It's a subset of A cross A, so it's a set of ordered pairs.
Mhm.
First and second coordinates, both coming from A. Says find the transitive closure. So, every ordered pair that's in there, we're gonna include. All right. Now,
Okay.
F is using the graph, and we can do that too. But the idea here is that if you think about 0, 1 and 1, 2, we need 0, 2. So that was what I drew on the board, and we can look at that now. We have a path, an edge from 0 to 1, and an edge from 1 to 2. So we need the shortcut edge from 0 to 2. So we need 0, 2. That's the, so 0, 2 gets added, right? There's also a way to get from 1 to 2, then 2 to 3, 1, 2, 2, 3. So that's two sides of, of a triangle. We want the shortcut from 1 to 3. So 1 to 3 got added. And 1, 2, 3, 4, 5, but they added something else. Because once we add the edge 1 to 3, then we can get from 0 to 1 and 1 to 3. So we want the shortcut from 0 to 3, and that's where that other ordered pair came from, right here in the middle. Does that make
Mhm.
sense?
Yeah.
So yeah, you're supposed to put them all. So, I mean, that's another way that we could have analyzed this problem. If we started with this, I'll stop sharing. Another way to analyze this problem, here's the original relation. It's kind of a big one, right? Because I just picked this out of our review. But if we draw the directed graph for R1, remember I said it's called an arrow diagram or a directed graph. I could probably directed graph is a better way to name it, because that's the name she uses. So it is a directed graph. So starting again, using the directed graph approach, the original R1. So here's 1, here's 2, here's 3. And we talked about this in class. You don't have to arrange them like that. But all right, so we have the loops 1, 1, 2, 2, 3, 3, and 4, 4. They're all there, but they're not going to play any role whatsoever in transitive closure. So I'm not going to draw them. Okay.
Mhm.
But we have an edge from 1 to 4, an edge from 1 to 2, an edge back from 2 to 1, an edge from 2 to 2. That's the loop. We'll skip that. An edge from 2 to 3. The loop from 3 to 3, I'm not going to draw it because it doesn't play into trying to find transitive closure. And we have the edge from 4 to 1, and then the loop 4 to 4, I'm not going to draw here. So not drawing the loops for the little a, comma, little a ordered pairs, because it's just not helpful here. We will, of course, include those ordered pairs in the final answer because they're part of the original relation. But now, so let's see if we can understand it. All right, so let's just start at 1. Where can we get to from 1? Well, we can go from 1 to 2, and we can go from 2 to 3. So we want the shortcut from 1 to 3. So we're going to add 1, comma 3. Okay.
Mhm.
We can get from 2 to 3, and we can't go anywhere from there. Okay. So, oh yeah. Okay, so we can get from, let's say, we can get from 4 to 1 and 1 to 2. So we want the shortcut to get directly from 4 to 2, right?
Yeah.
And we can get from 2 to 1 and 1 to 4. We want the shortcut directly from 2 to 4. Now let's see what's going on. We can get from 2 to 4 and 4 to 1. So we need to be able to get directly from 2 to 1, but we already can do that. What else? We can get from 4 to 2 and 2 to 3. So what do we want?
4 to 3.
Yeah. Notice a bunch of arrows point to 3, but nothing comes out of 3, right? So that's never, so let's see, 4 to 1, 1 to 2, we got the shortcut, 4 to 2. 2 to 1, 1 to 4, we got the shortcut, 2 to 4. 1 to 2, 2 to 3, we got 1 to 3. And then we've got, oh yeah, this new one, 4 to 2, 2 to 3. So we want to get directly from 4 to 3. Yeah, and 2, 5, yeah, and 2 to 4 and 4 to 3, but we have the shortcut from 2 directly to 3. Yep, that's it. And that is 4 edges. So, add the red ordered, the red ordered pairs associated with the new red edges. So that's the way that we use the directed graph to check for transitivity. So which way do you like better? Do you like the directed graph way better, or do you like the algebra way better?
I like the first way better.
You actually like the algebra way better.
Yeah.
It's nice that we have 2 different ways to do it. It is easy to kind of get lost in these graphs, right? Like
Yeah.
you feel insecure. Like, did I really find every path of length 2? Like, 1 to 2, 2 to 3. It's a path of length 2. This is length 1. This is length, 1 again. So 1 plus 1 is 2. Did we really find all of those? So we would get the shortcut path directly from 1 to 3. I can understand. So it's nice that we have both ways to do that. All right, let's so let me just say, if you want some more practice, right? It certainly wouldn't hurt you to go ahead and look at the next relation in the chapter 8 review. And let me just yeah, why don't you go ahead and do later, find the transitive closure of R2.
Okay.
You feel better about that now?
Yeah, I do. I was like having trouble, I was like unsure when I should flip the ordered pairs.
Always, if you
Like,
can.
yeah.
All right, next question, somebody else. Chloe, I think you were in here first.
He can go first. I'm reading over some stuff.
Cool. Suleiman, it's all you. What would you like to talk about?
I just have some questions on the one-to-one and onto.
All right.
Yeah, so I was just kind of like, I wouldn't say confused, but there was a specific question on because I was on the chapter 8 section with the chapter 5, 8, and 11. I think that's what it is. There was a specific question that says,
Are you asking, no, problems? Are you talking about functions or chapter 8? So functions is chapter 7.
yeah,
Chapter
wait,
7. So are you talking about particular problems on the chapter 7 review? Is that what you're talking about?
yes, yeah.
Oh, I'm sorry. I misunderstood. Yeah, let me grab that chapter 7 review
Yeah.
on functions. I guess I named it differently, didn't I? I just said
Yeah. It's the
review.
test 3 review of functions.
Yeah, I should rename it chapter 7, shouldn't I? But anyway, I mean, all you have to do is look at the notes or, you know, have attended lecture and you know, chapter 7 is functions.
Yeah,
So
yeah.
let's take, so the review. Test 3. And what problem was the first problem that you want to look at?
I was
Or-
looking at no, like number two,
And
2A.
2A.
Yeah.
So, may I ask you this, Suleiman?
Yes,
Have you had a chance to view the video that's posted for chapter 7 lecture?
no, I haven't.
Well, do you think that you might want to do that before you start you know, grabbing solutions? Don't you think that you should uh watch the video, or
No, no.
have you looked at the notes?
Yes, I have.
All right.
I
So
already answered all the questions. Like from number one, I already answered all the
oh, so you're feeling
questions.
pretty good about, so you
Yes,
know the,
I feel pretty good about like learning like is a G a function from B to C. I just want you to like at least work on it so I can see how you're doing it and just understand, okay, this
so
is
what
how
are the properties? Can you give me the definition? Can you finish this definition? Let's see. A function f from A to B. Let's just make sure we know the definitions. Let's do 1-to-1 first, okay?
Mhm.
Because you got to, you know, we got to know the definitions. A function, and we'll talk about the intuition too. A function f from A to B is 1-to-1 if, now, can you tell me the rest of that definition?
If every element in A matches B.
That's the definition of a function, that every element in A maps to one element in B. And it is really easy to get the definition of function confused with the definition of 1-to-1. Let me help you out. It's if every element of B has at most one pre-image element back in A that pairs with it. In other words, we write it this way technically. If f of A1 equaling f of A2 implies that A1 is actually equal to A2, and this is for all elements, little a1 and little a2, of course, from the domain A. And the intuition here that goes with this definition is this. In the arrow diagram, for F from A to B. And do you understand arrow diagrams okay?
Yes, ma'am.
Great. In the arrow diagram for F from A to B, there is at most one arrow pointing to any given element little b in the codomain B. So at most one arrow pointing to a B. Okay, and now this is the kind of the picture intuition. But if you want to think about the algebra intuition, where we're thinking about F as a set of ordered pairs, because that's what it is, when we examine the ordered pairs in F, each element little b in the codomain big B appears as a second coordinate in at most one ordered pair. In other words, we don't want to see any little b appear as the second coordinate in two different ordered pairs. So here's an example. Let's define, let me just go ahead and say A is going to be the set with 1, 2, and 3 in it. And B is going to be the set with little x, little y, and little z in it. And we're going to let F from A to B be this set of ordered pairs, where 1 pairs with x, 2 pairs with y, and let's say 3 pairs with z. Okay? Now we can draw the picture. So we can do this 2 ways. Here's A and here's B. And here's 1, 2, and 3 over in A, right? And so we draw the order, 1 is going to X, 2 is going to Y, 3 is going to Z. So using the intuition for the arrow diagram, there's at most 1 arrow pointing to any given element over here in B. And if you look at any given element, look at X or look at Y or look at Z, there is at most 1 arrow pointing to each of those. Okay, now, no, at most 1 arrow points to each element little b in B. But if you want to think about the intuition from the algebra point of view, each element little b in B, we're talking about X and Y and Z, appears as a second coordinate in at most 1 ordered pair. See, X appears as a second coordinate in at most 1 ordered pair. It only appears in this ordered pair as the second coordinate. Same with Y, same with Z. Does that make sense?
Makes sense.
So F is 1 to 1. Now, let's check G from A to B, where G is 1 is going to go to X, 2 is going to go to X, and 3 is going to go to Z. So if we drew the arrow diagram for G, you see what's going to happen here? One points to X, 2 points to X, 3 points to Z. So if we think about the arrow diagram approach, there's at most supposed to be at most 1 arrow pointing to any element in the codomain B. Well, there's at most 1 arrow pointing to Z. So far, so good. If we're going backwards, there's at most 1 arrow pointing to Y because there aren't any arrows pointing to Y. That's fine. That doesn't hurt one-to-oneness. We didn't say there has to be an arrow. There just has to be at most 1 arrow pointing to any element in the codomain. But X has 2 arrows pointing to it, and that breaks the 1-to-1 requirement, because you see F of 1 is equal to F of 2 because they're both equal to X, but 1 is not equal to 2. So we have F of A1 is 1, is equal to F of A2, little a2 is 2, but A1 is actually not equal to A2. And that's the negation of the definition of 1-to-1. 1-to-1 says if F of A1 equals F of A2, then A1 and A2 actually have to be the same element back in A. See? But if you let A1 be 1 and A2 be 2, F of A1 equals F of A2. They're both pointing to X, they both map to X. But A1 is not equal to A2. 1 and 2 are 2 different elements. Now, if you prefer not to do the picture or even the definition, but look at the set of ordered pairs, look at X. It appears more than once as the second coordinate of an ordered pair. But you see, for it to be F to be 1-to-1, each element, little b and b, appears as a second coordinate in at most one ordered pair, at most one ordered pair. But here X is appearing as a second coordinate in 2 ordered pairs. So this G
It's not
is
on.
not. Does that make sense?
Yes, it does make sense. Makes
And
so much.
that's the deal with 1-to-1.
Okay.
Now, do we need to go through onto with the,
Yeah. If that's okay.
it's okay?
Yeah, that's okay.
Okay. And again, if you
No,
look at,
I was saying that we can go to onto as well.
so normally when somebody says that's okay, it means, don't bother. But when you're saying that's okay, you mean please do, right?
Yeah, that's what I mean. Sorry, but
No, I'm just letting you know that that's okay usually means skip it. That's fine. We'll do it. So, functions, properties, continuing our discussion here. Onto. So again, we want a definition. A function f from a to b. And by the way, these properties don't make sense if we're not talking about a function. And these properties don't apply to like a binary relation that's not a function. A function f from a to b is onto if each element little b in the codomain capital B has at least one pre-image in A under the function f, i.e., for all B in B, there does exist an A back in the domain big A such that A, B is in F, or we could say, i.e., such that F of A is B. And so if we want to think about intuition, we can think about a picture, thinking about the arrow diagram. In the arrow diagram, for F, there is at least one arrow pointing to each element little b in the codomain B. So we need at least one arrow pointing to each B. Whereas for 1-to-1, we have to have at most one arrow pointing to any given B. You see?
Yeah.
And then if we want to think about the algebra, you want to think about F as a set of ordered pairs. Viewing F as a set of ordered pairs, each element little b in the codomain B, where we're, shooting for, this set we're shooting for, appears at least once as a second coordinate of an ordered pair in F. So every element over here in B, again, we can just use A equals a set containing 1, 2, and 3, and B being the set containing little x, little y, and little z. Again, if we use this F where 1 maps to x, 2 maps to y, and 3 maps to z, right?
Yeah.
Then each element in the codomain does get hit with an arrow. Right? Every single x, well, excuse me, little b, whether it be x or y or z, gets hit by an arrow. Each little b in b gets hit. Gets hit. Gets hit. We're going to get hit. We're in Mississippi. We're going to get hit by at least one arrow, as opposed to at most one arrow. And if we think about the algebra, then each element in B does appear as a second coordinate at least once. Now I want to do a different example here. I'm going to let A be the set containing 1, 2, 3, and 4, and B can still be the set containing X, Y, and Z. And I'm going to define H from A to B like this. H is going to be the map where 1 maps to X, 2 maps to Y, 3 maps to Y, and 4 maps to Z. Okay. If we draw the arrow diagram now, our A's got 4 elements in it. Maybe I should have called it C or something. It doesn't really matter. It's a different problem. We've got an arrow from 1 to X, 2 goes to Y, 3 also goes to Y. That's okay. We're just trying to hit everything. It doesn't matter if we hit it more than once. You know what I mean?
Mhm.
Each element of B gets hit by at least one arrow. Each element of codomain B appears as a second coordinate at least once. So H is 1, 2. But H is not 1 to 1 because something gets hit by more than one arrow, namely Y. And that breaks 1 to 1-ness, but it's definitely on 2. Everything gets hit. Let's look at one more example. Let me show what it looks like to have function that's not on 2. We just need to miss something, right? We just need to make sure that we don't hit everything. So we can use the same A and the same B, even though A is bigger than B, we can still make a function that's not onto. K is going to go from A to B, and K is going to equal, well, let's just send 1 to X, and 2 to X, and 3 to Y, and 4 to X. All right. So when we draw that arrow diagram, 1, 2, 3, 4, does everything in B get hit by an arrow?
No, Z does not get it.
That's right. I like to think of onto as like a wall-to-wall carpet that's completely onto the whole floor. It covers it up,
Okay.
right? And so if there, if these arrows don't completely cover up the codomain, in other words, the range, if the range, which are the elements that actually do get hit by arrows, the range isn't equal to the codomain, B is the codomain, right? Then it can't be onto, because we missed something, right? Z has no arrow that hits it. Also, when you look at these ordered pairs, Z does not appear as the second coordinate in even one ordered pair. So K is not onto. Is K 1 to 1?
Wait, are you asking me a question? Sorry.
Is K 1 to 1?
Uh, it's K 1 to 1. Yes.
Let's review our intuition behind 1 to 1. Lamont, you missed class, but you are allowed to bring a cheat sheet tomorrow. You may want to include the definitions of onto and 1 to 1. A function is 1 to 1 if in the arrow diagram there is at most one arrow pointing to any given element in the codomain. And if you want to think of the algebra, when we examine the ordered pairs in the function, whether it's called f or k or whatever, and each element little b in the codomain, each element little b in the codomain appears as a second coordinate in at most one ordered pair.
So it's not 1 to 1.
That's right.
Okay, gotcha.
Because, right? Because X is hit by more than one arrow. Does that help?
Yes.
So I strongly suggest that you do go, please now, and watch those. See, you're missing class, right? How are you feeling, by the way? I know you had a car wreck and a
Yeah.
concussion.
Yeah. I'm feeling
So-
okay. I've been resting a lot, so that's what mostly I've been doing, and just using medications and stuff that my mom
Oh,
gave.
you're using medication?
You said,
Generally, really? What for? For a headache?
just for the pain, because I have a lot of like back pain and stuff like that,
Oh,
and
no. How
a little bit,
terrible.
a little bit of back pain, and yeah. So,
Oh, how terrible. Because that's going to affect your performance. Did you ever go to the ER?
no, it wasn't like I was like feeling like I was about to die. It was just a lot of
No,
pain.
I'm not saying that. The problem is, just for future reference as a student, if you
Mhm.
are in an accident and now you're taking pain medication and you've had to rest, and we're sneaking up on what's the equivalent of a final exam. If you had gone to the ER and gotten a doctor's note saying, yeah, you have a concussion, then that's grounds for an incomplete.
Okay.
But I know that costs money. I get that. And it's a tough choice. But just for future reference, okay?
That's right. Gotcha.
You're welcome. Watch those videos. The links are, do you know, you found these review sheets, so you've seen the links to the videos
Yeah.
okay? And so the lecture that you missed, that video is already up.
Okay. I'll definitely watch those.
And
Okay.
chapter 5, I mean, I think you might have missed part of some chapter 5 lectures because you know,
I mean, chapter 5, I'm really caught up on.
great.
Yeah.
So it's chapter
So
7 and chapter
it's just,
8, and
yeah,
you'll
it's
be
just chapter
fine.
7. Yeah. I'm really
Perfect.
caught up with the induction and the sequences part and the terms one with the n factorial and all that. I'm caught
That's
up with
great.
those.
That's great.
So yeah,
So,
it's just chapter 7 and 8 I just need to focus.
well, generally speaking, just as a matter of etiquette,
Yeah.
you come into an office hour after you've watched, looked over the materials that are available. But I'm happy that we went over this because this may help all of the class that watches it.
Yeah.
But in general, that's your responsibility, is to know the definitions. I mean, that's like a minimum thing that you are responsible for in order to make the most of office hour time. Does that make sense?
Yeah, it makes sense. Makes sense.
Cleo, do you have any other questions?
Thank you so much.
Welcome.
I do. I guess the last thing I wanted to ask about was finding equivalence classes when you're not given ordered pairs.
So did you run into some WebAssign problems?
Yeah. Like I got the question, like, when they give you what the ordered pairs just fine, but
Well, I think there was an example where they gave you a set though and a rule, right? So let's let X be this set. 0, 1, 2, 3. In fact, let's back it up. Let's say, were there some negative numbers in the set and WebAssign as well, or did they start at 0? Do you remember?
it went from -3 to +5.
All right, so let's go from -4 just to be a little even extra careful. And in the example in WebAssign, was the divisor D equals 3 or 2 or 4, or do you remember?
It was 5 divides like m squared minus n squared.
Okay, so let's say curly R is a relation on X, so it's a subset of X cross X. This is an X with ears. Is defined by the rule that 4 divides m squared minus n squared.
Mhm.
In other words, m is R to n if and only if 4 divides m squared minus n squared for all elements little m and little n in X. How does that look? Let's try that one. All right. So we could just warm up with a few questions like, is -4 R to 1? Is -4 R to -2? You see what I mean?
So you would just start with an x and then compare it to
Some
like,
other right.
okay.
True or false? So let's just see if we can sort this out. 1, -4 is R to -4. Let's just see if it's related to itself. All right. So let's do our scrap work and let's see if we can figure it out. So we're asking, does 4 divide -4 squared minus -4 squared, right? What is negative 4 squared?
16.
So does 4 divide 16 minus 16? But that's really the question. Does 4 divide 0?
Yes.
Yes. And in fact, 4 will divide 0. And if you should take any of these elements,
Mm-hmm.
square it, and then subtract that same element squared, can you see we're always going to get 0 and 4 will always
Yeah.
divide it? So for any x in this set, big X, x4 will divide x squared minus x squared because x squared minus x squared is always equal to 0 and 4 always divides 0. So that's actually an argument for reflexivity. This is actually a proof that curly R is reflexive. We've just proven that any element is curly R to itself because that element squared minus that same element squared is always 0 and 4 divides 0. And this won't matter whether it's 4 or 5 or 3 or 2. 0 is divisible by every non-zero integer. Any divisor is going to divide 0, any legitimate divisor. So we know that each of these is going to be related to itself, and that's good because it's an equivalence relation. It better have reflexivity. It's going to also have symmetry. So let's take a look at some other elements. Is negative 4 R to negative 3? Is negative 4 R to negative 2? Like maybe we can figure out what the pattern is.
Mm-hmm.
Is negative 4 R to negative 1? Is negative 4 R? Let's just kind of see if we can figure out what negative 4 is related to, and we might be able to kind of see a pattern. So what are we going to be checking to see if negative 4 is related to negative 3? We're checking to see if does 4 divide negative 4 squared minus negative 3 squared, right?
Mm-hmm.
In fact, let's just look at negative 4. Let's not make this a statement. Let's just look at the expression. Negative 4 squared minus negative, what is that?
16 or 16 minus 9.
Which is,
7.
and 4 does not divide 7.
Yeah.
So whereas this was true, that negative 4 is related to negative 4, negative 4 is not related to negative 3. What about negative 4 and negative 2?
It'd be 16 minus 2. Or 16 minus 4. Yeah.
16 minus 4, right?
Just 12.
And does 4 divide 12?
Yes.
Okay, so negative 4 is related to negative 2. Let's see if, so negative 4 is related to negative 4. It's related to negative 2. What do you think the next one is it'll be related to? Do you see, do you sneak up, do you dare venture a guess about the pattern yet? Or do we have to look a little bit more?
Not yet.
That's fine. That's why we're looking. All right, let's see. Is negative 4 related to negative 1? Let's check. Is negative 4 squared minus negative 1 squared going to be divisible by 4? Well, what is negative 4 squared minus negative 1 squared?
16 minus 1 is 15.
And does 4 divide 15? Of course not. Right? What is it? So negative 4 is not related to negative 1. Now you go ahead and check and see if 4 is related to 0.
It is.
Right, because we're just looking at 16.
Mhm.
And 4 does divide 16, doesn't it?
So is it like every even number?
Kind of think, yeah, I think all the evens are going to probably be related to each other. And all the odds are going to probably be related to each other. That's kind of what I'm thinking. Like, you know, I don't really want to check them all. So I'm kind of thinking maybe we might, but that's kind of the conjecture that the evens will be related, right? And the odds, we might be able to prove that by using the definition of even and the definition of odd. Let's just explore that. So M is R to N if and only if 4 divides M squared minus N squared. And that was where we have this, you know, big set X, where it's, you know, -4, -3, -2, dot, 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 to 4, 5, 6. I made this, you know, big enough, right? So continuing with this example, here's our conjecture or our claim or question. If M and N are both even, is M going to be related to N? Let's see. Let's just do some scrap work and see if this might scrap for a proof, not a counterexample, but I'm just not going to write a formal proof, but I'm just going to try to convince myself. If M is even, right? If we assume M is even, then that means M is equal to 2K, right?
Yeah.
And if N is even, we can call N, you know, what? What do you want to call N?
2J.
Why not? Can you see it?
Mhm.
You see what's happening? Now let's look at M squared minus N squared. What is M squared minus N squared? Well, it's 2K quantity squared minus 2J quantity squared. But isn't that 4K squared
Mhm.
minus 4J squared?
Yeah.
Isn't that going to be 4 times an integer K squared minus J squared? So indeed, 4 divides M squared minus N squared if M and N are both even. Now, we can't just automatically assume that because it worked out when M and N are both even, that it's going to work out when M and N are both odd, right? We
Mhm.
kind of like to check it out. So here's a question. If M and N are both odd, is M going to be related to N? All right, so, you know, we can try, you know, using this definition of curly R and see if we can get 4 to divide the difference of M squared minus N squared. So if we assume M is odd, then M is equal to 2K plus 1. And if N is odd, we can certainly say N is equal to 2J plus 1. And now let's look at M squared minus N squared is equal to 2K plus 1 quantity squared minus 2j plus 1 quantity squared. Let's go ahead and unravel this. This is 4k squared plus 4k plus 1 minus the quantity. See, this is a minus.
Mm-hmm.
2j times 2j is 4j squared plus 2j plus another copy of 2j is plus 4j. And then plus 1 times plus 1 is plus 1, but this minus is, going to eventually change that to a minus 1. See, when we distribute that negative, these two are going to cancel, lo and behold.
Okay.
So it looks like the odds are all going to be related to each other. And the evens are all going to be related to each other, like I'm convinced now. Because this is this is a general proof. So yes was the answer, resounding. Indeed, So yes is, and so the equivalence class of -4 is going to be the same as the equivalence class of -2. These are all the same equivalence class. It's the same because they're in the same equivalence class. Their equivalence classes are the same.
Yeah.
And so what is that equivalence class? The equivalence class of 4, this is just sort of a notice. They might have just asked you for some of these, but the point is they're all the same. When elements are related by an equivalence relation, their equivalence classes are the same class because they're all related to all the same elements. That's what it means to be related. So -4 as an equivalence class has the evens in it.
And then all even numbers would have the same exact equivalence class, right?
That's right, for this
Yeah.
particular relation.
Mm-hmm.
Right, and the odds would all have the same equivalence class. But in fact, you might just be asked to find the equivalence class of 3, or you might be asked to find the equivalence class of -2, or right. But the point is, no matter which one you're asked to find. And by the way, you know what? Let's use the canonical representative. I haven't really talked about that much, but when we're talking about the evens versus the odds, there is a canonical representative for the evens, generally speaking, and this set does have that canonical representative, and there is a canonical representative for the odd numbers, and this set, that we're playing with does have that as well. What do you think the canonical representative would be for the set that we call, 2Z or the evens?
I don't know. I think we talked about this once.
Well, let me ask you a few leading questions. When we're playing games about even versus odd, right? Parity, P-A-R-I-T-Y, the parity of an integer is its evenness or oddness. When we're playing parity games, even odd games, what is the divisor that we're playing with?
2.
So when we're dividing by 2, what are the two important numbers?
It's remainders if it's
That's
0 or 1.
And so 0 is the canonical representative for even numbers because 0 is the remainder that all of them give when you divide them by 2. And what do you think what should we name this?
1.
Yes.
Okay.
Just a few leading questions. Very nicely done. Chloe, do you have a question? It's your turn.
I think I'm good. I'm eating up all this advanced stuff that we're gonna learn tonight.
Yeah, that's right.
I think I'm good for now. I'm gonna head out and make my cheat sheet.
That's a good idea. Making a concise cheat sheet is just such a smart thing to do.
It's just like a normal, like regular piece of paper, right? Like
8 and a
Like a
half
blank
by
piece of
11.
paper.
It's one side.
Mm-hmm.
I did write one side, right?
Yeah, you did.
I better send an announcement out tonight to remind people one side. Because you know what? You know what? I think we all know what.
Can it be like a paper line paper like this, like what you have right here on
8 and a
your
half by 11. 8 and a half by 11. Which is just regular notebook size, one side. Okay. So I'm going to send out that announcement now to remind people. One side only. And if somebody comes in with two sides, I'm going to take it away from them and they're going to hate my guts. And see, no good deed goes unpunished. Just for your information, students. No good deed goes unpunished. I promise you that. On test 2, I asked parts A and B of numerous questions to try to help you with, I'd ask part A to try to help you with part B, right? Like write the contrapositive. Part B, write a proof by an appropriate method, right? But in part A, I asked you to write the contrapositive, or maybe I asked you to write the contrapositive and the negation. At least you know it's going to be one of those two methods, contrapositive or contradiction. But sure enough, I had a student complain about, oh, there were so many parts on the questions. It was confusing. And I'm like, wow, I thought it was a gift. No good deed goes unpunished. By the way, ladies and gentlemen, I'm sure you've gotten your emails because I know you read all your TU emails, but the student evaluations closed today. So I guess I better shoot out an email about that as well. All right. I'm going to call it a break until 6. See you then.
Okay. Bye.
right.
Thank you.
You're very welcome.
Thank you.
Welcome. Thanks for playing.
All right, see you later, Professor.